Welcome to our exploration of the myth of normality in statistics. We'll delve into the assumptions and misconceptions surrounding normal distributions and their impact on statistical analysis. When calculating probabilities, like scoring at least 80 points on a test, we often assume a normal distribution. However, if the distribution isn't normal, this assumption can lead to inaccurate results. In classical statistics, computing the probability is the same as computing the area of a shape. However, when the shape is not what we assume to be, the computation becomes inaccurate. For example, if the width of a square is 4 meters, then the area is 4 multiplies 4, which is 16 squared meters. But what if the shape is irregular rather than a perfect square? In this case, the area is not exactly 16 squared meters. By the same token, what if the area of a distribution does not form a perfectly normal distribution? There's a common misconception that converting raw scores to z-scores can normalize a distribution. In reality, if the original distribution is skewed or heavy-tailed, the converted scores remain non-normal. Real-world data often deviates from normality due to skewness, heavy tails, or outliers. For instance, income data is typically right-skewed, while biological measurements may have heavy tails, challenging the assumption of normality. Some people argue that we don't need a perfectly normal distribution in a single dataset. In classical statistics, the probability is computed by assuming that the same study is repeated over and over in the long run. Thus, we can put our faith on the central limit theorem, CLT. According to CLT, for a sufficiently large sample size, the sampling distribution of the statistics will approach a normal distribution, regardless of the population's underlying distribution. This is why parametric tests, which often rely on the normality of sampling distributions, can still work with non-normal populations. Actually, it creates a false sense of security. For messy and noisy distributions, which are likely to happen in the real world, much larger samples may be needed to achieve a reliable approximation. However, the sampling distribution is still an approximation of normality, not the exact normality. For example, even if 100,000 samples are drawn from a non-normal population, and there are 25 observations in each sample, the sampling distributions are not symmetrical. Carl Pearson criticized the normal curve's fitness for describing errors. He highlighted that normality isn't inherently suitable for natural deviations, challenging its widespread acceptance in statistical practice. Gabriel Lippmann and Stigler criticized the circular logic of normality. They pointed out that both mathematicians and experimenters mistakenly believe in normal approximation due to its perceived mathematical and experimental validity. Carl Gauss's concept of the mean using least squares assumes normal distribution of errors. This circular reasoning suggests the mean is most probable only if deviations are normally distributed, reinforcing the myth of normality. In 1947, Geary argued that normality is a special case, not a universal property. Despite this, the dominance of Fisher's school led to the favoring of universal normality, sidelining interest in non-normal distributions. Geary proposed that textbooks should warn that normality is a myth, as there never was a truly normal distribution. Unfortunately, this warning has largely been ignored in statistical education and practice. Understanding the limitations of normality is crucial for accurate statistical analysis. Recognizing the diversity of real-world data distributions helps in choosing appropriate methods and avoiding misleading conclusions. It is better to explore the patterns of the data at hand rather than making strong assumptions. I hope this insight encourages you to adopt a more critical approach to data analytics.